Okay, and then so this is going to be like, you know, how we will proceed. I think this time, if you submit a day late or something, it's still okay. But try to be on time from now on. So it's kind of like a warm-up assignment to see if everybody knows how to use the system and knows how to find the assignments, and everything works out, hopefully. We are in negotiation with the departments to find a bigger room. I'm really sorry that nothing has happened yet, but I'm very hopeful, and like seeing that it is like literally we have 2 chairs left now. This is fantastic. This is okay. We'll probably, or quite certainly, have to find something else. But let's hope that this comes around soon. Today, before we start about today, is everything from last time clear to you? Are there open questions that you would like to ask right now? No questions, no nods. Okay, so I hope that everything is clear. The assignment was, and like, any questions or some interesting stuff that you found? Some comments? Okay, nothing. Good. Today we're gonna like focus in. So last week we had like a broad discussion about, okay, these are typical machine learning problems. These are the different approaches. We briefly talked about supervised learning. There's going to be more of that today. We mentioned unsupervised learning, kind of the opposite of this. We mentioned briefly reinforcement learning, etc. But today we're going to focus on supervised learning. And the outline of the lecture, and also kind of like more or less of or some sort of kind of a list of things that I would like you to get or to take away from this lecture today, because I am kind of like sometimes, so in these lecture outlines I'm putting some broad topics that I want you guys to know about. They will likely be part of some homework or some assignment or some questions in the exams, etc. So these are, you know, like I'm giving hints. I'm not telling you the questions directly, but these are kind of hints. So what we want to know, or what we have to do today, is like a thorough understanding of characteristics and the definition of supervised learning. So that you know what is supervised learning, what is unsupervised learning. We're not talking about unsupervised learning today, but like this is what we need to do today. So the capability to identify supervised learning problems based on like real-world problems. So we bring a few real-world problems, but you can imagine. So if you have like a topic or a task in a job or in other classes, etc., are you able to identify, hey, this is a typical supervised learning problem. I can approach that with a supervised machine learning algorithm. We're going to talk about hypotheses and hypothesis spaces. We're going to define empirical errors because so hypothesis and hypothesis space basically the realm where machine learning algorithms or supervised machine learning algorithms are actually living in. We're going to define this, and we're going to define empirical error because, as you might know, classification or supervised learning tasks, we want to reduce or minimize a certain type of error. We talk about what an empirical error is, or what an example for an error is. We're talking about the VC dimension, also the Vatnik-Charbonenko dimension. It's kind of like an idea of a measure for assessing like how powerful a machine learning algorithm is, or how expressive a machine learning algorithm is. Hey. I think there are 2 seats right there, or maybe the one 2 there. But, Then we're going to define and try to understand PAC learnable problems. So PAC means probably approximately correct. And we're going to talk about evaluating and conducting a machine learning experiment. And I should have added here that we're also, maybe not this week, but we're also going to look at the difference between classification and regression. So that's a different style of problem, even though regression is also supervised. So that needs to be added here. Okay, so supervised learning. We have had this picture last week as well. So this is our algorithm here. We want to make this one really strong and good. This is our input data, and these outputs need to be of some sort, right? Like they need to approximate something. And in classification, they need to approximate or like predict a class or a category. So you have 3 different types of flowers. I give you the features of the flowers, like the characteristics of the flowers. Is the flower red? Is the flower blue? Is it like, does it have round petals, or is it like more of an oval-shaped petal? So these are the features that go in, and based on these features, I want to know if the flower is an iris or a daisy flower or whatever, right? So that's kind of like classification. In regression, we want to have this as like a real valued output, so it could be just a function that we learn here. Then we discussed the fact that we have the hidden variables that we want to learn, that we want to manipulate and change so that they make a good approximation. And then we have these model parameters that we need to validate for. And we're going to discuss today what this validation means. You don't have to like know about this yet, but the model parameters could be, for example, the size of a neural network. I guess everybody has heard of deep learning, right? So, but how deep is deep? So I don't know if you know about this. So deep learning means that there's a number of layers, right? Let's say 5 layers. Is that deep? Probably. Is 2 layers deep? Maybe. Not really, probably. But then 3 layers, it starts to get deep. But then, like, what is the optimal depth for a machine learning algorithm? Hey, and so in deep learning, we don't know it. We just have to try it out. We need to do trial and error to find out which depth or which model parameter works best. And so, for example, the number of layers would be one of those model parameters. Okay. But now there's the last thing that we need in a supervised learning problem. Is called the teacher or the target signal. And we call it T in this case. And we get information about it at this stage here. So the target is what this should be like, okay? So this is our prediction, but the prediction should be as close to the target as possible, okay? And you can already guess that the distance between those two is going to be our error or our performance metric, okay? So we want to optimize the distance between those two. And it should be as small as possible. Okay? Is that clear? So, good. And so, again, based on a sample or training data, so we get a lot of these X's with a lot of these T's, right? We get a bunch of X's with their labels, so we get a number of, like, let's say 100 examples of flowers with their features or characteristics, and then we also get the same number of targets, like 1s or 0s for iris or daisy flower, or we get 1, 2s, and 3s if we have 3 classes, and so on, okay? So that's our data sample or training data. And they're given class labels or categories. It's possible to train a system that can generalize over unseen data. And so now that's the big question, the generalizing over unseen data. So now we train the system, but then like now we have a whole different pool of data points that are out there, and we want to know what these are, but we don't have labels for them, for example, right? So we give them to the algorithm, and the algorithm gives us an idea or a hypothesis on what they are, okay? So that's kind of like what we want to do in these machine learning or supervised learning algorithms. And again, to bring back this function here, we have training data with the machine learning algorithm, we generate the hypothesis, we look at how good the hypothesis works on the training data, right? And we give feedback to the machine learning algorithm about this so that we can adapt our parameters and then maybe have a better hypothesis. And in the end, we just put in the test data where we don't have labels for and see what the hypothesis spits out, okay? So that's kind of like the overall idea of supervised machine learning. Now we're going to go into more like of a more specific example of that, okay? So in this case, we have this two-dimensional example, and this is all from the Alpidine book. You can like read up on most of the stuff that I'm talking about there. So now, can anybody identify what the features are on this slide? Or it says there. Yeah. So the features are our x and y axis here, okay? So this is engine power and price, okay? So these are the two input features, x1 and x2. Our target class is family car or not family car, okay? And family car is denoted with these pluses here, and not family car with a minus, okay? So now, can anybody give me a hypothesis of like what defines a family car? And you can use price and engine power to do so. So you can see that family cars seem to be more like in the middle here, right? So on a high level, you could say a family car seems to be in the middle of engine power as well as price range, right? So something like that. Okay, that could be a hypothesis. It's pretty vague, but if you give this problem to a machine learning algorithm, it might find something more accurate or more precise. So one of the hypotheses could be if price is greater than this value here and smaller than this value here, as well as if engine power is greater than this value here and smaller than like this value here, then we have defined a family car. And what you get is kind of like a rectangle out of here, okay? That's kind of what a machine learning algorithm could find, okay? We can, okay, so this is kind of easy, but yeah, so we can also define a circle. That's something that we could do too. And then, so these are all negative examples, these are all positive examples, just like for illustration. The input is composed of these two, and the labels are zeros and ones, so this is kind of like just summing up what this represents. And now our training data for the machine learning algorithm are these two together, okay? For all of these points. So it's like this sample of observations and labels, okay? And we have n samples, so 2, 4, 6, 8, 10, 12, 14, 15, so n is 15, okay? And so this is our training data, okay? And now the test data, you could imagine like I get an observation and it falls here, right? So the algorithm would say, could be a not family car. But if it falls here, it's probably family car. And our algorithm will need to make these definitions or these decisions. So, as I mentioned, this is a example hypothesis. Okay? So, like, and it's defined by these two thresholds here for price and these two thresholds here for engine power. Okay? So, how many model parameters or hidden variables does this like example hypothesis have? So how many variables does the machine learning algorithm that produces a hypothesis like this need to learn?
2.
2? It's 4, right? This is 1, 2, 3, and 4. Yeah? And then the hypothesis looks like this. Right? So we need to learn these 2 and these 2. Okay? So that's all we have to learn for this, and that's kind of like the hypothesis space of having 2 intervals that define something. That's a hypothesis space. So like if I have the ability to find 2 thresholds on each feature, that's kind of like what my hypothesis space looks like. And this can be named as like the hypothesis of all rectangles, okay? I can define any rectangle with 4 thresholds, and that's my hypothesis space. Is that clear? All right. So the learning algorithm ideally finds these thresholds to approximate C, which is the target class, which is family cars. And it approximates it as good as possible. And the hypothesis output is 1 if the observation X given into the hypothesis H produces a 1 or a 0. Okay, if it's positive or negative example. That's our hypothesis. All right. So, do you know other possible hypothesis spaces? So we had a mention of like 3 parameters, right? So what would that hypothesis space look like? Or 3 thresholds? It would kind of look like a triangle, right? So we could do this, this, and that. So we could like span triangles and stuff like that in here. So we had 3 thresholds there. We could do, what else could we do? It doesn't have to fit perfectly. That's one thing. It doesn't have to solve it.
Ellipse.
Ellipse, yes, very good. So it would be something like this. What would be the parameters for that?
Range of A and B for the ellipse.
Yeah, so you would have like for the extreme radius for
minor axis and major.
Yeah, exactly. And we're going to talk about these. So these are called radial basis functions. What we usually have in the radial basis function is a center point and like the variance or standard deviation, and that could be like a diagonal variance, or it could be just one value, which would make a circle. If you have multiple values, you can make an ellipse. You can make something like arbitrarily shaped with that. So that's great. What is the most simple one that you can think of? Rectangle is the simplest one? Circle is quite simple, but it could be a line, right? So something like this, or that, right? So that's a little bit simpler. Okay, and we're going to talk about like what it means to have something simple versus something complex. So this is kind of like the topic for today. So, in principle, this is kind of like just as I mentioned here. So like these 15 observations are probably much smaller than the actual space of all the legal observations that we could have. We could have a lot of dots up here, like up here, Lamborghinis and stuff like that, so they're definitely not family cars, but this is kind of like the interesting space, and this is the training data that we have. And we probably will get, what would happen? We'll probably get a lot of like observations that might, you know, end up in here or in there. And if we use this hypothesis here, we can make errors. We can make mistakes, right? So if something falls in here, it's a mistake. If something falls in here, it's a mistake, because this is the actual, like, you know, definition of it. And we often need to approximate this class through H, and the quality of our approximation is measured based on the empirical error, and the empirical error is defined as basically the sum of all my mistakes. Okay, so if I make mistakes in my classification algorithm, that counts as an error, and then I count how many errors I make, and that's kind of like a measure for how well the performance is. So this symbol here basically counts a 1 if this is fulfilled, okay? So if my hypothesis is different than the target, okay? So for this training set, like any rectangle that has only pluses in here and only minuses outside will always make 0 errors, okay? If I pull a diagonal through here and say everything that's above the diagonal goes like this. Everything's above the diagonal is a family car, everything below is not a family car. I would make 1, 2, 3, 4, 5, 6 errors, okay? So we count it that way. And now the interesting part becomes when we want to generalize, right? So we want to create a hypothesis that is as accurate as possible, but also as general as possible. So for every unseen data point, I want it to be as good as possible, okay? So I can create, as we discussed, we can create many hypotheses. We can create circles, triangles, we can create different types of rectangles. Well, I want to find the best one, okay? And so there's kind of like a concept that we need to think about. So we need to find the best hypothesis, but many solutions are perfect in this case with 0 error. And the choice of threshold is important, as we can see, as future examples may not be part of, like, or may not follow what we see here. So I said, like, there, with error 0, we can create this rectangle here. It's very close to all these observations. But I can also create this rectangle here that's very far from these representations, okay? So that's kind of like the widest one versus the most specific one, okay? And everything in between them are legal and good hypotheses that create 0 error. But which one is the optimal one out of these? And if you think that these two dimensions here, engine power and price, are continuous or real valued, then you could have infinitely many legal solutions, okay? So which one is the right one? And there is kind of like an idea for that. So as I said, this is the most specific one, and the outside one here is the most general one that makes 0 errors. But this here is actually the real class, okay? The C. But we don't know this, right? We only have these observations that look like this. But we want to get to the C. So which one will we choose? Will we choose S or will we choose G? We would choose neither, I guess, or probably. And so the ones that we would choose are, so what would be, so we haven't seen every data point yet. So there might be a data point that is a family car, but it's here, right? So the specific one is wrong. And we haven't seen all the non-family cars, so we might get an observation that's here, and it's not a family car, right? So it's both like G and S are either too specific or too general. So it's something in the middle, but which one or what characteristic would be the best to have? And the best characteristic to have is kind of intuitive. It's actually the one. So if you count this one as on the border and this one as on the border, right? So you want to kind of have something that is exactly in between the ones that are on the border of the classes. So, and here the same. So this one is the border, this is the border. So we want something that's exactly in the middle here, because then I can have all of these observations here and all of these observations here, and they would all be correct. Okay? So the distance between any data point and the boundaries of the classification, which is this, and these are all boundaries, that's called the margin, and we want to maximize the margin. It looks like this. So this is the optimal hypothesis H here, because it has the maximum margin here, and it's always equal distance. So the margin is always, or like the boundary, the optimal boundary is always equally distant from this guy as well as this guy. Okay? And the same for this dimension here. So we have the maximum border here, and the maximum one here, and the maximum one here. Okay? So these things are called maximum margin classifiers. And I think the most famous maximum margin classifier is the support vector machine. And the support vector machine is famous for this because it optimizes this margin automatically. So anything that you throw at it, it will optimize for this. And that's a great feature to have, because it gives this optimal hypothesis. And the cool thing about the support vector machine is it only needs support vectors. It doesn't need anything else. And these gray ones here, they are on the border, right? And these are the ones that are support vectors. If you have a million more down here, they don't matter, because only the ones on the border are important. So I can remove all of these 4 down here, I can remove these 2, I can remove these 3, and still the exact same classification or hypothesis result will come out, right? So that's kind of cool with the support vector machines. But we'll discuss support vector machines quite a bit later, but in a lot more detail. So this is kind of like what we want to get. So the intuitive choice could be the hypothesis maximizes the so-called margin. So this is the margin. This is the margin, okay? Margin is the minimal distance between the separation boundaries. This one and this one. And the nearest sample point in X. So this is like this point, or this point, this point. All right. Cool. So now the question that I have here is, so we have, so I mentioned that support vector machines optimize for the margin. Would they be able to do so if they use this empirical error here? That gives you 1s if you misclassify it, and 0s if you don't misclassify it. So the error is just the sum of all the errors I make. And it's just a number of errors I make. It doesn't, right? What would we need to do something like finding the optimal margin?
Euclidean distance.
Yes, very good. So we need to have something like a distance metric from the decision boundary to the observations that we make. And the further away our observations are from the boundary, the better it is. Because if they're all very, very close, we like just a little bit of more noise, you know? Like I might have made this observation wrong and the price is actually not like exactly 15,000, but it's 1,499 or 14,999, something like that, okay? So I might have made an error in the observation, but that would misclassify it already. So we would need a a distance metric, right? So that's great. And the distance metric could be Euclidean distance, could be Matlab distance, whatever. Like anything that accounts for a distance between like the decision boundary and the data point. Okay, so sometimes it's not possible to find an optimal hypothesis. That is very important. I think you should underline this. Like, if your results in any exercise or you know, class project or whatever gives a result that does not have error equal 0, don't freak out. Because I would freak out if it actually says it's equal 0, because that would be definitely something would be wrong. Okay, most of the time, like most of real-world examples or real-world tasks are not perfectly solvable. It would be weird if they were. Like, why would it need our work if it was possible? So if we choose petal width and sepal length here, this example, what could be our hypothesis space? And in this case, we want to classify the red ones. We could make a circle. I saw a gesture back there. We could also, in this case, we could make a line through here. That'd be nice. We can again make like a square. In this case, if we want to separate the blues from the rest, we will make a little bit of an error if we do like a, you know, like a square. So we have like a couple of blue ones that are in the middle of the green ones, so we couldn't make like an easy separation. These are all pretty cool examples, and in fact, you will solve this at home. And this is going to be like the second week assignment to do this classification. There is a complete walkthrough of this in the Matlab introduction or the Matlab documentation. So it's not very hard to do. It's more of like trying to do as much Matlab coding as possible in the very beginning. I would try to not completely copy everything, but try to write it down yourself. I don't want to see like just copied everything out, but because Matlab is actually, they have a nice documentation about this, but they're actually making a couple of mistakes, and we'll come to this in a second. What they do wrong, because they don't conduct an actual machine learning experiment, they just use all the data for classification and for training and for testing, okay? But we're not going to do this. Excellent. So, any questions until here? Alright, so we're going to start with the real cool topics now. Statistical learning theory. That's the moment when everybody should leave the room. So, statistical learning theory, and this is only going to be a little excursion, but I think it's important to like kind of understand what's going on in this topic. So, and we're talking about the VC dimension, the Vapnik-Chervenenkis dimension, and in this case, we just basically assume that a data set contains n samples. So let's say we have 3 samples, 1, 2, 3. And if we have 3 samples, we have exactly 2 to the power of 3 many possible ways to label them, right? They could all be blue, they could all be red, just one could be red, just one could be blue, it could be a different blue, it could be a different red one. So we have 8 possible labelings for a data set that just contains 3 data points, right? So that's the like first important like step that we need to take. So if we have 4, it's 2 to the power of 4 many learning problems that can be defined. Okay, and this will, like the number of data points and the number of possible labelings will inform us like what type of hypothesis we need to have to be able to separate everything. Okay, and we'll get to this. So, this is another definition that we need. So any learning problem defined by n samples, if that happens, can be learned with 0 error by a hypothesis drawn from H. And if any of these problems can be solved by a hypothesis H in H, then the hypothesis space H shatters the point. I'll explain that in a second with an example. And the number of points that can be shattered by H, the hypothesis space, is called the Scherer dimension, or short VC dimension. Okay, so an example. I don't want to bother you too much with this because it's much more clear with an example. So we had the 3 points, right? I can separate these 3 points with a line like so. I can separate them like so. I can separate them like so, like so, like so, 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 so. Okay? So what we could say here is that the hypothesis class or hypothesis space of lines shatters at least 3 points. So the Vapnik-Scherer dimension is at least 3, right? Okay, what happens if we have 4 points? Can I find any configuration of 4 points that a line shatters? I can find this configuration where it's not possible. Can you think of one where it is possible? Easy answer is no, there's none, because that would be weird. But I can show you, I need to show you one thing though first. It's important to note that a line cannot always shatter all 3 points. So we can have 3 points that are on an exact line. So this could be a class or legal labeling. I can separate it like so, but if this would actually be the labeling, I couldn't just draw a line through it. So I only need to find one configuration of 3 points. So these 3 points, for example, or these 3 points. If I can find any of those, this shatters, like a line shatters this configuration. But I can find examples where it cannot solve it, but it's just because it's one line. But then that also means that the problem is a one-dimensional problem and not a two-dimensional problem. Okay. But I cannot find any 4 points where I can draw a line through and solve every labeling problem. So a line does not shatter all possible data labelings of any 4 data points in 2 dimensions. But this is important, it suffices that we can find a configuration. We don't have to find all configurations. It doesn't have to be true for all of them. So, well, I said it already, a 2D line is 3. What is it for a rectangle? So in a rectangle, again, we have 4 parameters. For a rectangle, it's actually 4. So we can solve this configuration of 4 points with a rectangle, for all the configurations. So this could be a positive, and these 3 negative examples. So we would draw the square somewhere around here, and so on. Okay, so it can be solved for 4. Now, more interesting, what's the Vapnik-Scherer dimension for a neural network that has, I don't know, arbitrary many parameters or layers or whatever? Important thing is we don't know. I mean, we don't know exactly. It's it's not very easy to know. So there's this very interesting machine learning paper called Dimensions of Neural Nets, and they have found like a very strict definition. So any functions that get inputs that are either +1 or -1, so they're only binary inputs, so that's already very restricting. And I can only make these operations plus, minus, times, and divide, so I cannot take any other, like I cannot make a sinus or a cosine or something like that of a function. And we can make these logical things like greater, equal, smaller, unequal, etc. And our outputs are 0 or 1. Now, the Viterbi dimension then is less or equal to 4d times t plus 2. So d is the dimension of computations that I can make, like how many operations I can make, and t is, what is t actually?
It's no more than t operations.
No more than t operations, so it's dependent on t, and then this is the dimension, like it's the dimension of the input, I think. When that computes. Yeah. So it's a parameter depending on like how many operations and how many like dimensions this function can have. So, but it's only an upper bound, right? For neural networks, it gets even worse. For feed-forward neural networks with 2 layers, we already have the O notation here. So we really don't know anything about like the exact Viterbi dimension for neural networks. And kind of you guess like what is the gist of this? Why do you even have to listen to this? Well, it's not very practical, so it doesn't really have something like an idea of a practical. Like I always take the algorithm with the largest Viterbi dimension because it's the most powerful one. There's no real practical value to this, but it gives you like a measure of like expressing how strong or how expressive a machine learning algorithm is. So we can like give an idea about the expressibility or expressiveness of a machine learning algorithm based on this dimension. We don't really need to know it for neural networks, but I think it's important to know that a line, for example, has a Viterbi dimension of 3, or a rectangle of 4, etc. Okay, so that's kind of like just the to give an idea of this. So it provides a measure of expressiveness or power of a hypothesis space, lines, rectangles, logical functions, etc. There's a maximum number of points that are shattered by hypothesis space, so we had that. And for more complex algorithms, only upper boundaries are provided, and no exact VC dimension is calculated. Couple of practical considerations that we need to make are, so the Viterbi dimension does not depend on the probability distribution that anything is chosen from. So, or these data points are chosen from. So you remember these 3 data points, we looked at all possible configurations, right? They could have been all blue, they could have been all red. Like each one of them could have been red or blue, so that's why it's like 2 to the power of the number of samples. In the real world, we don't have that issue. So it's not like if I have a linear classifier that only finds a line, can always only detect or like classify 3 points. That's not the case, because the real world is smooth. Like something that's close to something else is likely to be similar, right? So similarity is important. And in the VC dimension case, we don't assume this. Like anything could be labeled as anything. So in the real world, often neighboring samples have the same label, and we don't need to worry about all possible labelings, okay? This is very important. And so what this means is that hypothesis spaces with small VC dimensions are more powerful than one might think, okay? That's kind of an important gist. And so we can make a 10-minute break, come back at 3, and then we continue with pack learning.